Today, the main topic is going to be probability laws, which is chapter 2. So we're going to write down a bunch of properties. We'll still get plenty of practice with problem solving too. But we do want to understand things in an abstract way as well. We're going to find that a certain kind of diagram called a Venn diagram is useful, not only for solving problems, but for also understanding things in an abstract way. So we've got sample spaces, which are just sets, and events, which are subsets of sample spaces, representing things that can happen in a given experimental situation, like flipping a coin, or as we'll practice today, thinking about taking a card off a well-shuffled deck of cards. And we assign probabilities to different events. Some fundamental probability laws that we want to be true include the following. First of all, we want the probability that something in the sample space happens to be certain. For sure, 100% chance something in the sample space has got to happen. That's expressed by saying the probability of S, where S represents the sample space, is 1. Or 100% if you prefer. Of course, we talked about the weird situations of gorillas running through the room and grabbing your coin and things like that. Of course, we ignore those kinds of things, as I emphasized last week, for the sake of simplicity, for the sake of a simple model. And so this is part of our model, is the probability of S has to equal 1. S is the sample space. That's worth re-emphasizing it. That's the sample space. It is a subset of itself. Any set is a subset of itself. Of course, it also equals itself. But I could write S is a subset of itself. Every element of S is an element of S. So S is an event. Effectively, it's the event that something in your sample space happens. One of the outcomes in your sample space happens. Is this something that needs proof? No. What? I thought we have to prove everything in math. No, it's not true. Some things in math are what are called axioms. Anybody think they know what an axiom is? It's axiomatic. No? Nobody? Go ahead.
It's like a basic assumption.
It's a basic assumption. We're going to assume it's true. Wait a minute. Is that fair? Is that okay? Yes, it is, because you have to start your theory somewhere. Now, you might ask in an application, do I have the right sample space for that application? Because I am worried about a gorilla coming through the doorway. That's another question. That's a different question. For the purposes of the theory, we need to start somewhere. We need to assume something. And this is one of the things that we assume. This is an axiom. There's going to be 2 more axioms. We can still call them probability laws. They're still going to be things that you can use whenever you need them. Second probability law that is also an axiom is that probabilities are always greater than or equal to 0. The probability of any event A is greater than or equal to 0. That's an event. The events are subsets of the sample space as well. Any old subset of the sample space? This is actually a technicality that can get pretty complicated. If your sample space is finite, pretty much in every application I can think of, you'd want A to be any subset of S. But there are situations which we'll talk about where S is infinite. The sample space has infinitely many elements. And it turns out sometimes you want to not allow arbitrary subsets in such situations, because it gets extra technical for some extra technical reasons that I won't get into. It's like grad school level stuff. So I don't want to get into those reasons. We're not going to worry about those technicalities. For us, effectively, it's good enough to pretend A is an arbitrary subset of the sample space, and we're not going to worry about this. But certainly for any event, we want it to be non-negative, greater than or equal to 0. Should I say positive? Well, no, because 0 is actually not positive. 0, the number 0 is neither positive nor negative. So I shouldn't say P of A is positive because it could equal 0. But we don't want it to be negative, so it's certainly non-negative. Shouldn't I also assume it's less than or equal to 1? We'll come to that. I'm not going to for the moment. Law number 3 is if you've got a collection of mutually exclusive events. Read about this? Mutually exclusive means they can't occur at the same time. Then the probability of one or the other, or the other, or the other, or the other, etc., of those mutually exclusive events happening is the sum of their individual probabilities. If A1, A2, A3, etc., are mutually exclusive, what does that mean? It means if you take any two of them and ask what do they have in common, the answer is nothing. Their intersection is the empty set. AI intersect AJ is the empty set if AI and AJ are truly different sets, if I is not equal to J. That's what mutually exclusive means. AI and AJ can't occur at the same time in a given experiment. One could occur and not the other, or vice versa. It's possible neither one of them occurs either. Then the probability of A1 occurring, or A2 occurring, or A3 occurring, or A4 occurring, etc., which we denote by the union symbol, effectively, you can think of union as being synonymous with the word or. Effectively, union equals the word or. Okay, now don't take this equality too literally. Obviously, the union symbol does not equal the word or in quotes, but intuitively, effectively, whatever word you want to use, that's how we think of it. To be in a union of two sets, A or B, it does mean you are in one or the other. That's true. Or both. Though if they're mutually exclusive, you can't be in both. So union effectively means or. You find this probability by adding the individual probabilities. This skirts some technicalities as well. Like this list of the A's. Is that a finite list of events? I should probably put the word events in here. If these are mutually exclusive events, is that a finite list of events? Not necessarily, actually. Okay, if it's not necessarily finite, if it's infinite, you might wonder, does this infinite sum, oh boy, Calc 2, converge or not? The answer is effectively in writing this, we're assuming it's going to converge. And yeah, that also makes sense by the fact that the probability of S is 1. We can't get a sum bigger than 1 here. You might also wonder, is it possible that this list, this infinite collection of mutually exclusive events, maybe it's such a big infinity that you can't list them out? Wait, does that make any sense? It actually is a good question. We won't get into it. If you take real analysis, you talk about countably infinite versus uncountably infinite. There are different kinds of infinity. I am completely serious. And in fact, there's infinitely many kinds of infinity. That's just to entice you. Or maybe it turns you off. We don't have to worry about it, okay? For us, it's good enough to just say, maybe this is a finite list. Maybe I've got an infinite list that I can actually list out here. It's called countably infinite. These three laws, these three properties are all axioms. And they are the only axioms. Axioms of probability, we don't prove them, we assume them to get started on the theory. That's why. They give us our starting point. Again, you might have a random experiment where maybe you picked the wrong sample space, or maybe you've assigned probabilities poorly. You made a poor choice for how to assign probabilities so that these are not true. For example, if I'm flipping a coin once, even if it's a fair coin, if I decide heads is a probability of 0.8 and tails is a probability of 0.5, that's a bad assignment of probabilities. That property wouldn't hold. That would be a bad assignment. It wouldn't fit this. So for applications, you have to make sure you've done the right kind of thing. But as far as the theory goes, we start with these as assumptions and build from there. And you do want to keep your axioms as minimal as possible because the other laws that I'm about to write down should follow from these axioms. You should be able to prove what I'm about to write down next. The fourth law, see if I match the book's numbering, is that the probability of nothing happening is 0. The probability of the empty set, that's the empty set right there. It's not the Greek letter phi. I sort of made it look too much like a phi. You don't have to scratch yours out, but I'm going to try to make it a little bit more circular here for the oval. The probability of the empty set occurring is the number 0. And if you always put slashes through your zeros, you should try to make that slash a little bit more slanted. And the slash through this 0 should be maybe you should make your 0 more like this and the slash more like that if you happen to put slashes through your zeros. Okay, that's not the Greek letter phi or phi as some people call it. It's not a 0 with a slash through it, is the empty set. Nothing. By the way, the empty set is a subset of any set. There's the empty set. It is a subset of any set. Wait, what? How can nothing be a subset of any set? How does that make any sense? Effectively, it's a convention. It's a convention that's consistent with the rules of logic. For A to be a subset of B, every element of A must be an element of B. A is a subset, this is a definition here. A is a subset of B if every element of A is an element of B. I said that before, but I didn't write it down. As an implication, A being a subset of B means that if little a is in capital A, that implies that little a is also in capital B. I claim the empty set is a subset of any set. To prove that, I have to show that this definition works when A is the empty set. So I'd have to say, give me an element in the empty set and show it's an S. That's called vacuously true because there are no elements of the empty set. That implication that an arbitrary element of the empty set is an element of an arbitrary set S is automatically true because there are no elements of the empty set. Anybody take discrete math in here? Remember truth tables? What's a truth table for an implication? See if I can get this right. So you got P, you got Q, you got P implies Q. What is it? True, 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 false, false, true, and false, false. Oh, can I get this right? P implies Q is true in this case. It's also true in these two cases. It's only false in that one. These are the vacuously true cases. Effectively, you can think of them as being true just because it's convenient. It just makes everything work. I don't know if that's the best reason. But so if the P is false, it automatically means not that Q is true or false. It means the implication is true. P implies Q. And that's effectively what we got here in saying that the empty set is a subset of S. Because there are no elements of the empty set, so P would be false. Maybe you didn't have discrete math, so that's really confusing. Maybe you still did have discrete math, but it's still confusing. Don't worry about it too much. It's not something I'm really going to test you on, okay? This is not an axiom. You can prove this. So what is it? You could call it a theorem. Our book calls it a theorem. Theorems are mathematical statements that can be proven. Other names include proposition. It's such a trivial theorem, you might call it a lemma. Lemmas are kind of like trivial theorems that are useful for proving other things. Yeah. Well, we'll be consistent with the book and call it a theorem, but I'm not going to label it that yet. Property 5, probability law number 5 is if A prime is the set complement of A in S, does that mean derivative? No. Though it is derived from A, but it's not a calculus derivative. It is still derived from A. It's not the only notation people use. Sometimes people will put a C up there for complement. Sometimes they'll put the C in the front. Sometimes they'll like put a bar over A. The notation is wildly inconsistent across different math books. Kind of just depends on the author's preference. If A prime is the set complement of A and S, then the probability of the complement of A is 1 minus the probability of A, which is arithmetically equivalent to saying the probability of A is also 1 minus the probability of its complement. And the last rule we're going to write down right now is called the general addition rule. I suppose I should emphasize what a complement is. What is a complement? A prime is the set of everything in S, the sample space, that's not an A. In set builder notation, you write the set of all X in S. That little E symbol means is in or is an element of. It's really a Greek letter epsilon. The set of all X in S with the property that, the vertical line means, well, such that for short, or with the property that X is not in A. So if A is the event that it rains tomorrow, A complement is the event that it does not rain tomorrow. Actually, I should probably talk about rain today because they're forecast to have some big storms here in about 3 hours, 4 hours. So be watching for that. What's the probability of rain today? It sounds like it's going to be about 90%. So the probability that it doesn't rain today is about 10%. Makes intuitive sense. It is a law. It can be proved, though it's not an axiom. in a Venn diagram, which I hinted at but haven't drawn yet, if this box represents the sample space and A is that subset of the sample space, then A complement is everything outside of A, but still in S. A prime doesn't just depend on A, it also depends on what S is. But we don't write S in the notation. S is understood. What's the general addition rule? It says that in general, the probability of A1 union A2, remember, union means or. In general, whether A1 or A2 are mutually exclusive or not, maybe there's no overlap, maybe there is. Well, if there was no overlap, axiom 3 would imply the answer is this. But because we do allow overlap here, it's not the final answer in general. We turn out to have to subtract the probability of A1 intersect A2. Intersection, by the way, can be thought of as being basically equivalent to the word and. And that's kind of fortunate because it almost looks like an A, but don't make it an A. A1 intersect A2 is the set of all elements in both A1 and A2. We have to subtract off that probability from the sum in general. Now, if A1 and A2 were mutually exclusive, if their intersection was empty, no overlap in the Venn diagram between A1 and A2, they're two separate blobs that don't touch, then their intersection would be empty, and this would be the probability of the empty set, which would be 0. And so you wouldn't have to subtract it because subtracting 0 doesn't do anything. And so you don't have to write it in that case, which is axiom 3. But it's still true because subtracting 0 doesn't affect anything. So this general addition rule you do have to use when A1 intersect A2 is non-empty, but it's still also true even if it is empty. Does this thing make sense? A Venn diagram is not a proof, but it can help you make sense out of it. So once again, this box represents all of S. Maybe this blob here is A1, and this blob here with some overlap is A2. In Venn diagrams, you don't have to do this, but it's sometimes nice to do it. You can kind of think of the area as being the probability. So it's like you pretend the box itself, S, has an area of 1. Whatever the area of A1 is, looking at that, I could pretend it's 0.3. That would be its probability. Whatever the area of A2 is, did I make it bigger or smaller than A1? It's hard to tell. Let's pretend it's a little bit bigger. Let's pretend that area is 0.32. Then the probability of A2 would be 0.32. You're trying to find the probability of their union, meaning the total area when you combine A1 and A2. It's not 0.3 plus 0.32 because you'd be double counting the intersection, the area of that intersection. So to account for the double counting, you got to subtract it off. I'm explaining this saying you could think intuitively of probabilities as being areas in this diagram. Not that you have to do that. It's just convenient sometimes for the sake of understanding something like this. Not a proof, but to make it sound or seem reasonable. If you were thinking about a counting problem where your sample space is found with combinations and permutations as far as its size, then it's kind of like maybe I like to pretend S is like the gym floor in a gym, and maybe your objects in the sample space are people, and you tell them to stand in certain spots depending on whether they're male or female, whether they're above 6 feet in height or less than 6 feet in height. You know, you can classify them in various categories, whether they're in probability and statistics or not. And based on all those categories, you tell them to stand in certain spots at the gym. And to figure out the probability of, for example, A1 occurring, you count the number of people in A1 and divide by the total number of people in the gym. Right? That's like the classical formula if you've got equally likely outcomes. Another intuitive way to think about it if you want. Again, properties 4, 5, and 6 are not axioms, they are theorems. Theorems need proof. Why? Because we're not taking them to be axioms. Why not? Because we don't need to, because we can prove them from the axioms. That's why not. You want to keep your list of axioms minimal, as small as possible of a list. And once you got those axioms, you hope that along with logic is good enough to prove other facts that you hope are true or that you discover are true. These are all things that you would hope would be true in a sense, that make intuitive sense, but now you need to prove them. What should we do? How about we prove properties 4 and 5? And I will give you a proof for the assignment due Thursday that we'll take a look at, but I won't do that one in class. Let's prove properties 4 and 5. Proof that the probability of the empty set is the number 0. Technically speaking, proofs should be written in sentences. Will I do that here? Yes, I will. Do you need to do it for your homework? Yes, you should. This is pretty much the only homework assignment, though, where I'm going to require written proofs written out in sentences. There will be other things during the semester where you do need to verify something is true. You might call it a verification or a demonstration. It's not going to quite be up to the level of a proof. Giving brief reasons with different kinds of calculations will be good enough usually for us. This is not a proof-oriented class, but I do want to do a couple proofs today and give you one problem with a proof for your assignment. So a proof that the probability of the empty set is 0. What am I allowed to use? I'm allowed to use the axioms and I'm allowed to use logic. And like, what does the empty set mean? Well, it's the set containing nothing, and well, it's a subset of every set, that kind of thing I'm allowed to use. I'm also going to use a couple facts that technically require proof as well, though that they're relatively easy proofs. I want to set myself up to be able to use the axioms. What again are the axioms? The probability of S is 1. The probability of any event is non-negative. And if I've got a list of mutually exclusive events, the probability of one or the other, et cetera, is the sum of the probabilities. Somehow I got to use those. I think getting started on this proof is the hardest part. Like, how in the world am I supposed to use those when the empty set's not listed anywhere there? Well, these properties are still relevant. The probability of the empty set, I'm trying to prove it's 0, but I know from this axiom it can't be negative. That's a little bit of a help, I guess. Here's a more important key. The empty set is very much related to S itself. It's kind of like the opposite of S. It's the complement of S in itself. The complement of A in S is everything in S that's not an A. So I guess the complement of S prime would be everything in S that's not an S, which is nothing. Everything is an S. Everything in S is an S. The empty set is the complement of S. So the empty set is related to S. This fact must be relevant in some way. And in fact, if you union S with the empty set, you still get S, right? Union. union. Note that S union the empty set is S, and S intersect the empty set is the empty set. In other words, the empty set is the complement of S, though I'm not going to write that down because I'm not going to use that fact. I'm not going to use property 3 to prove property 4 because that would be cheating. I got to start with a first proof somewhere. Do these things need proof? Technically, yes, they do require proof. But I'm not going to bother. I hope they're pretty intuitive. S union the empty set is S. If something is in this union, that means it's an S or it's in the empty set. But nothing can be in the empty set, so it's got to be an S. Conversely, if something's an S, well, it's an S, so it's in this union. And those are really the reasons. If it went by too fast, you can rewatch this video when my phone says 35 minutes in. Why is this one true? If something is in S intersection, the empty set, that means it's in both S and the empty set. But nothing can be in the empty set, so that's effectively a contradiction. So that's really an argument by saying, pretend this is not empty and get a contradiction. If I pretend this is not empty, then something's in it. But to be in it, it means it's in S and it's got to be in the empty set. But nothing is in the empty set by definition. That's a contradiction. That's effectively a proof of that. You don't have to prove these basic facts about sets. I just very, very briefly verbally did so there. You can use equations in sentences. That's fine. You don't have to write these things out in words. Right? You can use equations within your sentences. What should I say next? I could say, but okay, I should probably say therefore. And by the way, 3 dots means therefore as well. You could use this as an abbreviation. Abbreviations are okay. I'll write the word therefore. Therefore, S and the empty set are mutually exclusive. I'm setting myself up to use axiom 3. So this is a little bit of a run-on sentence. Run-on sentences are forgivable. Okay. So what does that mean? I need to use axiom 3. The probability of S union the empty set is the probability of S plus the probability of the empty set. Find my sentence there. But the fact that S equals S union the empty set now implies that the probability of S is the probability of S plus the probability of the empty set. What did I do there? I just replaced that probability with that one because of this. You don't have to underline things and put arrows in your proofs. That's just for your benefit. All I did was replace S union the empty set with S. We're basically done. Okay, I should have done something else in here. I should have not ended that sentence quite so soon. I should have said by axiom 3. I should have said what axioms I used. Almost done. By axiom 1, right? It's got to be relevant that the probability of S is 1. Well, actually, this can be finished without that fact. I'll go ahead and use it anyway. P of S equals 1. So 1 equals 1 plus P of the empty set. I actually don't need the fact that that equals 1 exactly. It doesn't really matter what it is, because in this equation, it can cancel on either side anyway. But it doesn't hurt to use the fact that it equals 1. And this means that the probability of the empty set is 0. Done. QED. When mathematicians finish proofs, they get super excited and they start talking in Latin. Quadrant demonstrandum. QED. Being a Christian mathematician, I also often put PTL, praise the Lord. Okay. So either way is okay. When you end a proof, you have to do a little celebration. Okay. You can do a little dance if you want. That kind of thing. Yeah, we actually didn't need the full force of axiom 1. We didn't really need it at all. We could have just canceled P of S, subtracted P of S from both sides of this, and gotten right to that conclusion. Again, it doesn't hurt to use the fact that it equals 1. But we actually didn't need it. Interesting. You do need it for property 5, which we're about to prove. Actually, I won't prove property 5 completely for the sake of time. I'll just do a sketch of the proof. That means I'm not going to bother with sentences. Sketch of proof. Idea of proof is the teacher's way of saying, you know, I'm feeling a little lazy. Well, no, I'm not feeling lazy. It's I'm trying to save some time. Okay. So I won't write sentences to prove this. This equation, I already told you, is equivalent to saying P of A. It also equals 1 minus P of A prime. It's also equivalent to, this is not the proof yet. It's also equivalent to this fact. So if I can prove this fact, I've proved this one just by arithmetic, algebra. Yeah, let's just do the sketch of the proof. What's the idea? S does equal the union of A and A prime. A and A prime are mutually exclusive. Here's essentially one line of work that proves what I want to prove. 1 equals P of S equals P of A union A prime equals P of A plus P of A prime, and that does it. Over here, this is saying the fact that A intersect A prime is the empty set means A and A prime are mutually exclusive. So I can use axiom 3. The fact that their union of S, their union equals S, allows this equation to be true right there. And this equation is axiom 1. You really do need axiom 1 here. You do need the fact that P of S equals 1. For your homework, I'm going to assign a proof. What proof am I assigning? I'm going to have you prove, well, 2 things, actually. C and D in number 12. C is the harder one. D is easy once you use C. Once you've proved a theorem, you can then use the theorem anytime you need it. Not just for real-life applications, but also for other proofs. So you are now allowed in anything you want to prove for your homework to use not just those three axioms, but the three other properties, at least four properties, 4 and 5. 6 is a bit more complicated. You won't need 6 for this. You're supposed to prove part C here by applying axioms 3 and 2. You're trying to prove an inequality. That should seem a little scary. How do I prove an inequality? One number is less than or equal to another. A is a subset of B. So everything in A, every element of A is an element of B. You need that to finish the proof. Here it is in a Venn diagram. They do give you a hint there. Besides applying those axioms, they give you this hint. B equals the union of A with that set that is an intersection of the complement of A with B. Let's make sense out of this in a Venn diagram. We are assuming here again, A is a subset of B. The blob for A is inside the blob for B, and this is not a hole in B. Everything in A is also in B here. It's not a hole. A is a subset of B. So give me an arbitrary element of A, call it X, that implies that X is in B. It also implies that if X is not in B, then X is not in A. It also implies that. That's called the contrapositive. If P implies Q, then not Q implies not P. Discrete math thing again. These are both true. They mean the same thing, really. So you need that fact. And again, the book writes down the fact that you can write B as a union. A union with what? Union with everything in B that's not an A. The complement of A intersected with B is what is shaded blue there. That is a set with a hole in it. Besides these basic things and axioms 3 and 2, like they told you, what you need to realize here to help you finish the proof is that these two sets down here, A and A prime intersect B, are mutually exclusive. You can see it in the picture. A is right there. This set is shaded in blue right there. There's nothing in common. Technically speaking, this fact right here needs proof. You don't have to prove it. Technically, the fact that these two things I've underlined are mutually exclusive needs proof. You don't have to prove it. You may use these things to make your proof reasonably short. What else are you going to need? I'll let you see if you can figure that out. I'll give you one more little hint. It will be important that the probability of that is greater than or equal to 0. That's a pretty big hint. And that's one of the axioms. These are two mutually exclusive sets whose union is B. And this thing has a probability that's greater than or equal to 0. That basically does it for you, applying axioms 3 and 2. But you should write it out in sentences.